to the Fusion Talk series organized by Science and Silico Private Limited. This company is founded by academicians from IIT and NCL with a mission to bridge the gap between academic research and industry. We collaborate with both academic institutions and industry leaders to tackle challenges in drug and material discovery. And we take immense pride in being one of the first companies in India to develop an in-house drug discovery platform integrated with advanced AI capabilities. Our goal is to make drug and material discovery accessible to everyone, revolutionizing the scientific landscape and driving groundbreaking innovation. About the Fusion Talk series, it was born out of our desire to bring together academic and industry experts to share their valuable insights into the rapidly evolving scientific field. Through these discussions, we aim to foster knowledge exchange and inspire new ideas that push the boundaries of research and development. The speaker for today's talk is Dr. Salman Ahmad Khan. He's currently working as an assistant professor at Chemical Engineering Department, IIT Kanpur. He has received his bachelor's and master's from Chemical Engineering, IIT Kanpur. He has done his PhD from University of California, Santa Barbara, in the field of catalysis, studying reaction rate study theory, and rare events. Followed his PhD program, he has done his postdoctoral research with from University of Delaware, where he developed computational methods to model supported sub-nanometer cluster catalysts and machine learning tools to predict properties of hydrocarbon molecules. And today he's going to discuss about his research on catalysis, and the title of his presentation is Dynamics and Disorder in Catalytic Site-Ensembles. And now I hand over stage to Dr. Salman Khan to deliver your talk, and we will be looking forward to the interesting one. Yeah, thank you.
Yeah, thank you for that introduction, Anil. I just wanted to make sure you can see my slides. You see my slides, right?
Yes, I can.
Okay. Once again, thank you for that introduction. So today I'll be talking about some of the work that I've been doing in the last few years on modeling catalytic materials which are represented by site-ensembles, with space and time dependent site-ensembles. So I would like to start with a very simple introduction about categorizing catalytic materials into different categories based on the nature of their active sites. So on one end of the spectrum, we have these homogeneous catalytic materials like acid-base catalysts or organometallic catalysts, and even enzymes can be put into this category where you have the active center in a fluctuating environment. And we have statistical methods to average over these fluctuations. And using that, we can calculate free energies, populations of different reactants, products, and intermediates, and then also use that to calculate rates. And then we have this category of ordered heterogeneous catalytic materials, and examples of these can be very large nanoparticles of metals or metal oxides. We can have zeolites in this, or metal organic frameworks. And in these materials, the phase of the reactant and the products is different than the phase of the catalyst. So these are generally solid, and the reactants and the products are in the gas phase or in the liquid phase. So they have to diffuse to the surface and then do the reaction and then diffuse away. But because these materials are ordered, their structure is very well defined. It's easy to characterize them, and the number of active sites on their surface is also very limited in terms of the diversity of sites. They're pretty tractable to handle, and we have some pretty good frameworks to model these kind of materials. But we can add some disorder to this picture, and that leads us to this category of disordered catalytic materials, and there are a few different types. So over here, I'm showing you a couple of them. So on the top, we have these sub-nanometer clusters, which have very, very large configurational spaces. You can have these clusters in different sizes, different shapes, and also how do I remove this? Oh, yeah. And in some cases, they're also very dynamic, meaning that their shape changes while they're doing reactions. And on the bottom over here, I have an example of an amorphous catalyst where the distribution of sites on the surface is quenched, meaning it's a non-equilibrium distribution. And all of the sites on the surface have essentially different local environments. So the rates at which they turn over and the mechanisms by which they turn over are also very different depending on the local environment. So we have this gradual increase of complexity as we go from the left to the right in this picture. And in the last 2 or 3 decades, computationally, a lot of frameworks have been developed to model the first 2 categories, but not a lot of work has been done in modeling materials in this disordered category. And I've been spending some time working on developing methods and protocols to model these materials. And I'll be talking about a couple of different stories today in this domain. So I'll start by first talking about dispersed catalysts and specifically modeling sub-nanometer clusters. So if we think about supported catalysts in terms of dispersion and length scales, so these can be essentially metals which are dispersed on supports, which could be oxides or metals or some other type of material. So one end of the spectrum to the right, we have very, very large nanoparticles. So you have very large length scales, but very limited dispersion. And on the left end of the spectrum, we have the single atom catalysts where we have maximum dispersion, but then very, very tiny length scales. So you essentially have these single atoms, which are the active metal centers dispersed on these oxide supports. And somewhere in the middle, we get these sub-nanometer clusters. And interestingly, these clusters are active for a variety of reactions, even more active than these 2 other extremes for some reactions like propane dehydrogenation, naphtha reforming, etc. But the problem with these kind of catalysts is that once you synthesize them, you essentially do not have a lot of control over the distribution of these cluster shapes and sizes. So essentially what happens is that we end up with a very large distribution of cluster shapes and sizes, which is very sensitive to synthesis conditions. It's also very sensitive to operation conditions. It can change depending on the temperature, the pressure, the feed conditions, and so on. And because of that, it becomes very challenging to characterize these kind of materials. So one way we can get some information from experiments is using, for example, TEM measurements. So this can give us some information about particle size distributions. So for example, over here, I'm showing this particle distribution of a supported sub-nanometer cluster catalyst, where on the x-axis, we have the diameter, on the y-axis, we have the counts, meaning how many particles of each diameter you have. So you can get this kind of information from TEM, but essentially you lose out on any information about diversity within the same size. So we don't really essentially get any information about the shapes and the structure of these materials. So we can also turn to spectroscopic methods, but they also come with their own challenges for these kind of materials. So if we had materials which have very well-defined shapes, like the other 2 materials on this spectrum, like really large nanoparticles or single atom catalysts, which have very well-defined domains, we'll end up with very sharp features in their spectra. But when we try to probe these sub-nanometer clusters, which have a distribution of particle shapes and sizes, so we don't get sharp features in the spectra, and it becomes very, very challenging to back out their structure and their properties. So one workaround for this is we can look towards computational methods to model them. And typically electronic structure methods like density function theory, for example, is used to model these kind of materials and catalysts. But these methods are very, very expensive. And their application has mostly been limited to materials with very well-defined sites, like, for example, homogeneous catalysts or very large nanoparticles, which are essentially represented in terms of extended slabs. But when it comes to modeling these sub-nanometer clusters, it's pretty challenging to do that because, as I've said, that these clusters can take different shapes and sizes. So this is a disconnectivity diagram showing all the different possibilities of a given cluster size. So all the endpoints on this diagram essentially correspond to a different stable configuration, a locally stable configuration of the cluster. And so you can see that this has a very, very large phase space complexity. So it becomes almost impossible to explore this using these expensive electronic structure methods. And to this day, there are a lot of outstanding questions about these kind of materials, like what is the effect of temperature on these kind of distributions? How do adsorbates affect their distribution and structure? Is there any dynamical disorder in these systems, meaning like do they change in time depending on the process conditions and so on? So the status quo in the field has generally been to ignore all of this diversity and essentially take these single site models, which are very well defined. For example, you might start with a known configuration of a nanoparticle, put that on some support, and then try to model some reactions based on that. So essentially, you ignore all of the structural diversity and don't really look for stable configurations of these kind of sub-nanometer clusters. And I also want to point out that many of these questions are also a lot of research agencies, especially in the US and Europe, are very interested in answering some of these questions, essentially trying to learn about the complexity in catalytic materials. So now with that, I would like to begin my talk about the methods that I've developed to model these kind of materials and overcome some of these challenges. But before that, I just wanted to introduce the material that I will be specifically be working with for this particular part of the talk. So this is platinum dispersed on gamma alumina. So over here on this is the support on the bottom, gamma alumina in brown, and oxygens are shown in red. And on top of that, we have this platinum shown in blue, which is dispersed on the surface. So this is the catalyst which is active for a variety of reactions, including H2 dissociation, CO oxidation, but in the industry, it's also used for propane dehydrogenation. Over here, we also have the same problem. Once you synthesize this catalyst, you essentially have no control over the dispersion of these particles, these platinum particles on the gamma alumina support. And what happens is that you end up with a distribution of particle shapes and sizes. It's very challenging to model, as I've mentioned, with computational methods. So this is what we'll try to tackle. So the first thing that we want to handle is the expensive electronic structure calculations. So the idea is, so on the left, I'm showing you a top view of this system. So we have essentially the support, which is the alumina, and then we have these blue platinum particles on the surface. We calculate the energies and forces for a given configuration. We can do that using a lot of electronic structure codes. I particularly use density functional theory, for example, and then we can predict and calculate their energies and forces and use these energies and forces either to find local minima for these kind of materials, or then we can also use that for running some MD simulations. But as I've mentioned, these calculations are very expensive. So for that, we turn to some machine learning potentials. And the idea over here is that we can represent the local environment around atoms in some rotationally and translationally invariant basis, and then try to parameterize a machine learning model, which would be a neural network or a kernel regression model, by doing some DFT calculations. So essentially, we randomly sample a few configurations, do single point DFT calculations to get energies and forces, and that is a training set. And then we try to fit some machine learning model and try to predict energies and forces and try to bypass this step of this expensive step of calculating energies and forces using DFT. And this gives us a speed up of about 3 to 4 orders of magnitude for many systems. So this is how we try to get around this problem. But there is one other problem that still remains, which is the large configurational spaces of these clusters. So again, I'm showing you this disconnectivity diagram. On the y-axis, we have the energies of these clusters. So as you go down, the energy goes down, and the sites towards the bottom are more stable. And each point, as I've mentioned before, is essentially a stable local minima. So what we are essentially interested in is exploring these sites towards this the root of this tree, which are more stable. And for that, I use something called basin hopping. So it's a global minima finding algorithm, and it might be instructive to look at how it works in one dimension. So over here, we have a one-dimensional function which has 4 local minima. And the idea is we start from a random place on the function, and then we use some local minimization algorithm to minimize the function, and we find the local minimum, and then we randomly perturb this point. So in some cases, what is going to happen when you randomly perturb it, it's going to end up in the same local basin. But sometimes what's going to happen is that it's going to escape the basin, and we are going to discover a different basin and find a different local minimum. And if we keep doing this, the idea is that hopefully we'll start to discover these low energy states and try to find the global minimum of the system. So what we've done is we combined the machine learning and the basin hopping into one algorithm in an active learning algorithm. And the idea over here is that we start by first generating some random configurations of these platinum particles on the surface, train a preliminary machine learning potential. So I'm showing a parity plot of that on the top left, where on the x-axis we have the DFT energies, on the y-axis we have the predicted energies. This is the parity line, so it's working pretty well for the initial potential. Then we use the trained potential to run a basin hopping simulation, and we discover ensembles of stable platinum clusters. And then we recalculate their energies and forces using DFT. And then we have some criteria. If it's within some tolerance, we stop. If not, we take all of the clusters that we discover, put them back into a training set, retrain the model, and keep going around this loop until we converge. So once we've converged, we can look at how the basin hopping algorithm progresses and discovers stable cluster configurations. So over here, I'm showing you on the y-axis the energies of these clusters. And on the x-axis, we have the progress of the algorithm. And all of these trajectories are essentially different basin hopping trajectories fired from different locations in the phase space, meaning from different starting configurations. And there are about, I think, 20 of them in this plot. So in the beginning, we have these very high energy configurations. So over here, we have, again, the top view of the system. On the bottom, we have the alumina support, and these are platinum atoms. And you can see that over here, we have these disjoint domains in the beginning. As the algorithm progresses, we start to see some more stable configurations form. And eventually, we see the formation of these clusters as all of the particles come together. And finally, we start discovering these very stable configurations. And now the interesting part with these machine learned potentials is that once you have trained them, you can also explore the stability of other cluster sizes. So the one that I was showing you was platinum 10. And now we can extend it and look at the stable clusters of all other cluster sizes. So over here, I'm showing you the top view of the most stable clusters that we discovered from platinum 5 all the way to platinum 20. And over here, you can see all of these clusters have very different shapes. All the atoms have very, very different local environments and so on. And when we were doing this calculation, we discovered something very interesting, especially for these tiny clusters, about 5 and 6 atoms big, that these clusters interact very, very strongly with support. So in the middle over here, I'm showing you the side view of platinum 5, and you can see that it's embedding itself inside the support by breaking some aluminium and subsurface oxygen bonds. And on the bottom over here, I'm showing you the top view of the support without the platinum for clarity. And then I've colored all of the atoms by how much they've moved after we put the platinum on. So we can see that these aluminium atoms have popped out and they've moved by about 5 angstroms, 4 angstroms. So essentially, they're breaking a subsurface bond as the platinum is inserting itself inside. So now this is interesting because this Illumina model has been around for more than 2 decades now, and people have been using it for a lot of different calculations, especially in catalysis, but people have not really reported these kind of large support reconstructions when you put like these single or small clusters, single atoms or small clusters on the support. But there is some evidence from experiments, not exactly for this system, but a few other related systems. So over here, I have a couple of examples. So this is platinum and gold on the bottom, supported on titanium. And these are their TEM images. And you can see that these clusters are embedding themselves inside the titanium matrix. And this has a lot of implications, of course, for catalysis, because some of the atoms which go inside, they're not accessible to the reactants. And then this also changes their electronic properties. And it has a lot of implications for other things as well, right? So now to this point, using all of this framework, we were able to discover these stable configurations and then also look at some interesting features. But the problem with these machine learned potentials is that they have these very complicated basis functions, which we do not really understand. It's very hard to interpret. So the next thing that we wanted to do was really understand all of the stability and where it is coming from in terms of some human interpretable features. So for that, we turned to this Gini importance method, which can be implemented with random forest. And we wanted to explore some human interpretable features and how do they contribute to the stability of these clusters. So over here on the left, on the y-axis, we have the importance of the features, and on the x-axis, I'm showing you 5 features. So this is the average platinum-platinum coordination number, the sphericity of the clusters, the height, the average platinum oxygen, and the platinum-aluminium coordination numbers. So what we find is that this is not very surprising that for a material like this, the platinum-platinum coordination number essentially governs the stability of these clusters, and most of the variance can be explained by this feature. But the more interesting thing was that we can, using this information, collapse most of the data that we have on a very simple plot. So over here on the y-axis, we have the energy of these clusters per atom. And on the x-axis, we have the average platinum-platinum coordination number. And all of the points that you're seeing here, they go from blue, which is about platinum 5, to all the way to red, which is platinum 20. So you have clusters of different shapes and sizes in this. And we can represent this information with a very simple formula. It's minus 0.81 times the square root of coordination number of the average platinum coordination number. So even though you are missing out on some features of this distribution, but you're able to explain most of this data with such a simple model. So these kind of models have been reported before for very large nanoparticles, which are very well defined, and also for very large extended surfaces. But it was interesting to see that a model like that could also be applied to a system like this, which is a lot more complex with a lot more diversity in terms of cluster shapes and sizes. So now, to this point, we were looking at stability and looking at all of these features. But what we are really interested eventually in is how do these features affect, and how does this diversity in cluster shapes affect their activity? So I'm again showing you the top view of the most stable clusters that we have discovered. So again, to point out, all of these clusters, all the platinum atoms have very different local environments. So we wanted to look at how does this translate into some catalytic property. So over here on the right, I'm showing you a heat map of the turnover frequency of these of different platinum atoms from this distribution for propane dehydrogenation. So this is a log plot. And on the x-axis, we have the absorption energy of ethene. On the y-axis, we have the absorption energy of ethane. This heat map corresponds to the turnover frequency for propane dehydrogenation. So what we find is that small clusters are very active for this reaction. As you increase the size, the activity goes down by multiple orders of magnitude, as you can see in this plot. But the more interesting thing was that platinum atoms on the same cluster can have very different activities, which are different by multiple orders of magnitude. And by extension, also, if you have two clusters of the same size but different shapes, they'll have very different activities depending on the local environment of the platinum atoms. This is interesting because many a times experimentalists, whenever they synthesize and look at TM distributions and they see particles of the same size, they assume that the activity of these clusters are going to be the same. But this is a clear demonstration of why cluster shape can affect the activity in a very significant way. So this kind of brings me to the end of the first part of my talk. And before moving on, I'll be shifting gears a little bit after this. I just wanted to summarize this. Over here, we model these sub-nanometer clusters supported on oxides. And the problem is that these clusters have very, very large configuration spaces. So that makes it, one, very challenging to model using computations, and also very challenging for experimentalists to probe them using spectroscopic methods and microscopy. So we have developed this active learning algorithm combining machine learning and Bayesian hopping to discover stable configurations of these platinum clusters. And we discovered some very interesting features with this, where we found that these clusters can embed inside the support and changing their electronic and structural properties. And finally, we looked at the effect of these structural properties on the activity of these clusters. And we found that the cluster shape has, of course, a very big effect on the activity. As the cluster size increases, the activity goes down. But not only that, the shape also has a very, very strong effect on the activity of these clusters. So now with that, I would like to shift gears a little and then talk about the slightly different type of material, different type of catalyst. So again, I'm going to show you the same slide that I showed, same plot that I showed you in the second slide. So this is that dispersion and length scale plot. So over here, we were looking at supported clusters. On one end of the spectrum, we had these very large nanoparticles. On this end, we had these single atoms. But all of the supports in this case were crystalline. They were very well-ordered materials. But let's say if we look at this end of the spectrum, where we have these single atoms supported on crystalline material, but we add a disorder to this picture. So we end up in this domain of quenched disordered materials and like amorphous catalysts. So this is an example of that. So this is silica. And on top of that, these black atoms are some metal atoms that can be crafted on the surface of the silica. And this is these kind of catalysts are widely used in the industry for a variety of reactions, including epoxidation and also for polymerization to make plastics. But these materials, these distributions, they're represented by quenched non-equilibrium distributions, which are non-Boltzmann, and we don't really have any computational methods to model materials like this. So I'll be talking in my next part about how developing some methods that I worked on in my PhD to model these kind of materials. So there are different pieces to this problem, and it's a good idea to maybe look at them separately first. For these kind of materials, the first and the main part is looking at the support. So as I mentioned, silica is a commonly used amorphous support. So this is an atomistic model of amorphous silica, which is essentially just SiO2, a disordered form of SiO2, which is terminated by hydroxyl groups on the surface. And these hydroxyl groups are called silanols, and they can be of different types. So you could have vicinal silanols, where hydroxyl groups connected to a silicon share a common oxygen. You could have geminals, where you have two hydroxyl groups on the same silicon. Isolated silanols, you could also have siloxane groups on the surface. But other than these discrete categorizations, because this surface is amorphous, all of these categories essentially also have a lot of structural disorder in terms of different bond lengths and bond angles, and this affects their reactivity towards other molecules and influences their properties. So now once we have the support, The second step is we would like to synthesize the catalyst. And the way that it's done is typically you react the silica surface with a precursor, which could be in the gas phase or the liquid phase, like for example, TiCl4 or chromochlorate. And the way this reaction happens is, so for example, you have a couple of hydroxyl groups on the surface, a metal bonded to 4 ligands comes in contact with this, it eliminates 2 HL molecules and forms this bipodal metal species, which will be the active center for catalysis. And again, because as I mentioned, this surface is amorphous, so you have different local environments. So this is going to affect the thermodynamics and the kinetics of this reaction. So you might end up with different types of sites on the surface depending on the local environment. They might also graft at very different rates, which we will see in a second. But now once we have synthesized the catalyst, the last step is to study the catalysis. So I'm over here showing you the Phillips catalyst, which is chromium dispersed on amorphous silica. So this was discovered in the 1950s, and today it's used to produce about 50% of the polyethylene in the world. And there are still questions about the nature of the active site and the mechanism of this catalyst. And each of these, and again, in this case also, we have the same problem because it's an amorphous support. Every site has a different local environment. They turn over at different rates, and in some cases, they might also turn over at with different mechanisms. So each of these steps has its own challenges when it comes to modeling them. So the challenges with modeling these silica models is currently the models that we have, they're very, very small. And we don't know if they really follow experimental procedures. So it's very difficult for us to really say that the models that we have are representative of real silica materials. And when it comes to these two steps, the first problem is, of course, that we have this quench non-equilibrium distribution. So we have a lot of sites on the surface and we don't know which ones are real or are present in real materials. And also that these calculations have to be again done using expensive electronic structure methods. We don't, it's not feasible to do this for thousands of sites on the surface. Now, I'll be talking about a couple of different projects touching upon each of these points. So the first one is modeling the grafting of TiCl4 on amorphous silica. And they synthesize these TiSiO2 catalysts using this process, and these are active for epoxidation. And this is a very simple schematic showing the reaction. So in one flask, we have TiCl4 in the liquid phase, which is in vacuum, and then it's in equilibrium with its vapor. So they take this vapor and then they transfer it over into another flask, again under vacuum. And this vapor reacts with the silica. And you have silica in this material, it reacts with the silica, eliminating HCl, and then it grafts, the titanium grafts on the surface. So this is the proposed mechanism for the reaction. So there are a few different species here. So all of the gray species that you see are reactants, products, and the intermediates. And all of these species, which have a double dagger on top without the gray boxes, they are transition states. So the way that it starts is you have these vicinal silanols on the surface. You have a couple of hydroxyl groups. A titanium tetrachloride can come in contact with this, form through this transition state, eliminate HCl, and form a TiCl3 species. Then the other hydroxyl can also react with another TiCl4, eliminate HCl, and form a doubly monopodal TiCl3 species. And this TiCl3 in state 2 can also lean over, eliminate a HCl molecule, and form this doubly monopodal or this bipodal Ti species in blue over here. And 3 and 4, the monopodal and the bipodal, can also interconvert via eliminating a TiCl4 molecule. So this is a decently complicated reaction grafting mechanism. And if you want to model this whole process, there are different pieces and things that we'll have to consider from a computational point of view. So first, we need a model of the silica, an atomistic model of the silica. Second, we need to understand the free energies and the rates of this grafting mechanism. And again, as I mentioned, depending on the local environment, the free energies and the rates will be different. And finally, we would like to model the dynamics of this process because you have sites reacting at different rates on the surface at the same time. So now going to the first step. So we would like to generate atomistic models of amorphous silicas. We start with a bulk cristobalite structure, which is a crystalline form of silica. We heat it to a high temperature. So this melts the silica. And then we cleave it to generate a surface. And then we rapidly quench it to arrest it in an amorphous state. And now once we have arrested it in an amorphous state, we functionalize, we have a process to functionalize the surface to add hydroxyl groups. So this is how we generate our amorphous models of atomistic silica. And then we can do this process multiple times. And we generate hundreds of models of these silica so that we have a lot of sites on the surface. So we can converge the statistics for these kind of materials, as you'll see in a second. So now, once we have the silica model, the second step is to really understand the grafting process and the effect of the local structure on the free energies and the rates of this. So essentially, the local environment is defined by a lot of different things. You could have different bond lengths and bond angles influencing the free energies and the kinetics. But for this project, we only decided to look at the effect of these dihedral angles. So this is a model of the vicinal site, and this is the dihedral angle that I'm talking about, formed by this oxygen, silicon oxygen. And we looked at the free energies of the different species as a function of this dihedral angle. And what we found was that the free energies of these 4 species that I've highlighted, they're a very strong function of this dihedral angle, but these 4 species, their free energies was not a strong function. So we randomly sampled a few sites for different dihedral angles, calculated their free energy as a function of the dihedral angle. And I'm showing you that over here. So these are the 4 species. On the y-axis, we have their free energies. On the x-axis, we have the dihedral angle. And these are the polynomial fits to this data. And again, it's very simple one-dimensional fit. So it fits pretty well. And this is going to be our model to learn the free energy as a function of their dihedral angle. So now the next step is, once we have that, we would like to map the dihedral angle to the rate constants of this reaction, right? So over here, I'm showing you the reaction mechanism again without the transition state. So these are the 4 species, and we have rate constants connecting this showing the different conversions. And each of these rate constants is essentially a function of the local dihedral angle of the system, this one. And what now we can do with our parameterized model is we can calculate the free energies of all the species in the system, given a site with a fixed dihedral angle, calculate the free energies of all the species in the system, and we can calculate barriers. And then using that, we can calculate the rate constant using transition state theory. So now once we have that, we would like to model the dynamics of this reaction. And for that, we use population balance modeling framework. Again, the idea over here is not to really go into the details of these equations. It's just to show that we have these ODEs for all the species on the surface. So we have the rate of change of the coverage of the species, and you have consumption and production terms on the right-hand side, and you have that for all the species on the surface. The only thing that I would like to point out over here is that these are not only a function of time, but they're also a function of the dihedral angle. So this is not one equation. So each box is essentially multiple equations. It depends on how finely you discretize your phi axis. So in the end, we ended up with like 50 to 100 coupled ODE equations that we had to solve for the system. So I just wanted to point that out. So it's not 3, it's 3 times, however finally you discretize your phi grid. Now with that, we have all the pieces and we can put them together to model this whole process. So we start with the amorphous silica model that we generated. And from there, we extract a distribution of the dihedral angles. So on the x-axis, we have the dihedral angle. On the y-axis, we have their populations. So this is about 300 sites. So we generated multiple models of silica, and from there we extracted about 300 sites. So you can see that most of the sites have smaller dihedral angles, and then we also have a few with larger dihedral angles. It decays as the dihedral angle increases. And after that, we can take this distribution and do DFT calculations at a few different dihedral angles, parameterize a model to learn the free energy as a function of the angle. And then we can solve population balance model by parameterizing it with this polynomial fit. And finally, using the population balance model, we can predict the kinetics of the system. So this is the result of that. So again, over here, we have the mechanism of the 4 different species. And these are the 4 plots showing the evolution of the species as a function of time and the dihedral angle. So the way to read these plots is on the x-axis, we have the dihedral angle in all 4 plots. And on the y-axis, we have their fractions. And all of these plots have been colored from dark green, which is about 10 seconds on a log scale, all the way to light yellow, which is 10 to the power of 6 seconds. And you can see that the sites react at very different rates depending on the dihedral angle. So sites which have smaller dihedral angles, they react very fast, and sites with a larger dihedral angle react slowly. But not only that, the sites also react via different mechanisms. So if you look over here, what happens is that sites which have a very, very small dihedral angle, they go via 1, 2, 4, and then they go to 3. But sites which have larger dihedral angles, they directly go from 1, 2 to 3 without going to this 4th state. So we can clearly see, again, this is an example of how small changes in the structure can not only lead to changes in the rate, but also the mechanism of these kind of reactions. And now if you want to compare all of whatever we have predicted here to experiments, it becomes very challenging because experimentalists, of course, do not have access to all this fine-grained information. So what we can do is we can integrate over these plots and essentially look at the average populations of all the 3 types of sites on the surface. This is that plot. So on the x-axis, we have the time on a log scale again, all the way to 10 to the power of 6 seconds. On the y-axis, we have the average coverages of these species on the surface, so 2, 3, and 4. And we also have the pressure of HCl and torr, which is shown here in blue. So what you'll notice over here, a very interesting feature that we found was if you do this reaction for about 10 to the power of 3 seconds, most of the sites on the surface will convert to this bipodal Ti species. But if you were to wait for about 100 times longer, most of the sites will convert to this doubly monopodal Ti species shown here in red. And what is also going to happen is that once you have done this reaction up to 10 to the power of 3 seconds, you'll see that your pressure, which is shown by this blue plot, does not change much. So you might think that your reaction is stopped, but if you were to wait for about 100 times longer, all of these sites will convert to this singly monopodal species, doubly monopodal species. And this is interesting because this material has been synthesized in the 1980s multiple times since then, and people have reported all sorts of combinations of these species. So some papers have reported that all of the sites on the surface form this species 3, and in some papers have also reported this bipodal species, and in some have also reported a combination mixture of everything over here. So essentially, this kinetic trap reasoning could explain why there is so much controversy about the distribution of sites on the surface for this material. Right. So now with this brings me to the end of this part again, the grafting part of this talk. And I would like to again go back to this slide where we have talked about the amorphous silica. So we generated some models of amorphous silica, and then we developed ab initio parameterized population balance models to model the grafting and predict the evolution of the sites as a function of time. And finally, now once we have synthesized the catalyst, the most interesting part is we would like to study the catalysis by the synthesized material, right? So this comes with its own very unique challenges. So again, we of course have that problem of this unknown quench distribution, non-equilibrium distribution of sites on the surface. Again, we have to look at sites, multiple sites on the surface. So it's difficult to do calculations using QM methods. But the bigger problem in these materials is that experimentally it is known that many of these materials, only a small fraction of the sites are essentially responsible for all of the activity. And we wanted to tackle that problem. So the next part will be about that. But I would like to step back a little bit from real models for this part and show you this work for a very simple toy model. And you'll see in a second why we had to do that. Now I'll be talking about this a simple 2-dimensional model of silica that we developed. So this is a 2-dimensional uniform lattice. Then we take this and we add some perturbations to this lattice. So this introduces some quench disorder, and then we have a procedure of functionalizing the surface with the kind of groups that you would find on the surface of a real silica material like siloxanes, silanols, and also some grafted metal sites. Again, because this is a quench disordered environment, every metal site on the surface shown here in blue will have a different local environment. And we can zoom into one of these sites, and this is what it looks like. So on the left-hand side, we have the catalytic site. So we have the metal in yellow. On the y-axis, it's bonded to 2 oxygen atoms along the y-axis on the top and the bottom. And on the left and right along the x-axis, it is coordinating to these siloxane groups. Now, we also propose a very simple mechanism. So we have the species from the gas phase, which comes in and adsorbs on the surface of the metal. And this causes the metal to break a coordination bond. And then the species converts to B and it leaves, and we regenerate the site again. So this is a simple catalytic cycle for this toy model system. What we also do is we have parameterized Morse potential to model the interaction of the metal with the different species on the surface. So essentially what this allows us to do is optimize the structure of these reactants and products and also find transition states, just like how you would do it for a real system with an actual DFT or actual QM calculation. So this is going to be a proxy for actual QM calculations for this system. So now what we do is we generate a very large lattice and calculate the activation barriers for all sites on the lattice. So we have about 20,000 sites in our system, and which is now you can see that this is we cannot do 20,000 DFT calculations to calculate activation barriers. So we could do that for this system. So over here on the x-axis, we have the activation barriers, and on the y-axis is their frequency. And this is the distribution of activation barriers that we get. So if you are an experimentalist and let's say you want to measure the average activation barrier, or if you measure the activation barrier of the system, essentially you'll be measuring the average activation barrier of the system, right? But what happens is that because the rate goes as exponential of minus beta times the activation barrier, most of the sites towards this low activation barrier tail are going to dominate the kinetics. And you're going to measure something around close to this 40 kilojoule per mole number. So if you look at this distribution, most of the sites are towards this peak, but so they're very common, but they're inactive. They're not really doing anything. Most of the sites are which are active and important to us are very rare towards this low activation barrier tail. So how do we tackle this problem computationally? Like it becomes very challenging because sites, if you randomly start sampling sites and doing calculations for them, most of the sites that you will sample will be towards this peak of the distribution, and you'll learn nothing about the sites which are important and are really responsible for the catalysis. So for that, a couple of steps. Again, we turn to some machine learning. We would like to not do as many DFT calculations. So we try to represent the local environment of our system in terms of some geometrical coordinates. So over here, we have the bare site without the metal, and we represent it using these three coordinates. So the distance between the OH groups, D1, distance between the siloxanes, D2, and the angle between them, which is theta. So essentially, the environment is now represented by this three-dimensional vector, theta, D1, and D2. And we can randomly sample a few sites from our system, do DFT calculations to get activation barriers. And then we use kernel regression to learn the activation barriers as a function of these parameters. So we use this Mahalanobis distance to do this kernel regression fit. And this is essentially a weighted sum of the activation barriers in the training set, where the weights are defined by these exponential minus distance squared terms, where the distance is an extension of the Euclidean distance, and we are trying to learn this matrix S. So the idea over here is that if two sites are very close structurally, this distance is very small and the weight will be large. But if the sites are very different, the distance will be large and the weight will be small. And we use a leave-on-out loss to parameterize this model. But again, we still run into the same problem. As I mentioned in the last slide, we have this distribution which looks like this. And if we start randomly sampling sites, most of the sites that we will sample will be towards the peak of this distribution. So our machine learning model will essentially learn nothing about these rare and active sites. So for that, we've combined machine learning with importance sampling, and we call this importance learning. And the idea is we randomly sample a few sites from the surface, calculate actual DFT barriers, and then train a machine learning model on them. So over here on the x-axis, we have actual DFT energies. On the y-axis, we have the fit model for the initial pool of sites. And then we take our preliminary model and predict the activation barriers on all 20,000 sites, which is shown over here in blue. Then we take this distribution and we reweight it by the rate constants of the sites. And what this does is that it peaks the distribution towards the low activation barrier tail, as you can see over here, the one in orange. So now what we do is we resample a new site, but not from this blue distribution. Essentially, we sample a new site from this reweighted distribution. And we do another DFT calculation on this. And we have some criteria if the DFT energies are close to the model predicted energies, we stop. If not, we put the site back into our training pool, retrain the model, and keep going around this loop until we achieve convergence. And you can see that as the algorithm progresses, we start to discover sites, these red sites, which are towards the low activation barrier tail of this distribution. And you can see that it converges. Over here, I'm showing you the iteration on the x-axis. On the y-axis, we have the average activation barrier, which is essentially the experimental observable that we are trying to predict. And you can see that it converges very, very fast within 40-50 iterations. If we were to do this calculation by randomly sampling this blue distribution and doing DFT calculations, it would take us about almost 250,000 calculations. So at least for this system, you get an acceleration of about 3 orders of magnitude, even more than that. So now, of course, all of this was for a toy model, and now we've been extending this framework to some more realistic systems. So over here, this is an alumina surface again. So this is essentially not a catalytic cycle, but it's like a catalytic cycle. So we have this hydrogen hopping between different oxygen atoms on the surface of alumina. And again, so in this case, this is an amorphous alumina surface. And this hopping barrier depends on the local environment, and it can hop via two different mechanisms directly, or it can also hop in the presence of a water molecule via a shuttling mechanism. So we have this loop, which again looks like a catalytic cycle. And we can calculate the turnover frequency of this using importance learning, and then also random sampling and machine learning. And what we see is that importance learning converges very fast within 100 iterations. And as you can see that random sampling plus machine learning has not even converged within 300 iterations. And similarly, we can look at the errors, the relative errors over here. So this is on a log scale on the y-axis on the right. You can see that the importance learning errors essentially converge very fast within 100 iterations. And random sampling plus machine learning has still not converged even up to 300 iterations. So now this brings me to the end of my talk. Now we are essentially trying to extend this to, or my previous group is trying to extend this to more realistic systems and trying to calculate experimental observables for these realistic catalysts. And hopefully we'll see something more along those lines in the future. But now that brings me to the end of my talk. And I'd just like to end by summarizing this part. So I talked about these amorphous catalysts, where these are single metals dispersed on oxides like amorphous silica, and these are represented by non-equilibrium quench distributions. Essentially, we do not have methods to model these kind of materials. And so we've developed a couple of different protocols, ab initio parameterized population balance models to model the grafting of metal complexes on the surface of these materials, where we can look at the evolving populations of these sites. And as they're synthesized, and finally, once we have synthesized the catalyst, we've developed this importance learning algorithm to study and calculate the site average kinetics, which is the experimental observable for a system like this. And we've shown that the importance learning essentially gives us an acceleration of more than 3 orders of magnitude over brute force calculations. And now we are extending this method to more realistic systems. Now with that, I would just like to thank a few people, my postdoc and PhD advisors, Baron, Dion, and Susannah, and the University of Santa Barbara and University of Delaware, where most of this work was done. And right now, as I'm at IIT Kanpur, I have a really small group that you can see over here on the bottom right. And we're working on extending some of these methods and also in a few different new areas. And hopefully I'll have something to talk about the next time or some other time on the work from my own group. And with that, I would like to thank everyone. And then if you have any questions, I would be happy to answer them. Thank you.
Yeah, thank you, Dr. Salman, for the very interesting talk. Yeah, I would ask the audience to put their questions in the chat box if they have any. We'll wait for some time. Since we are waiting for questions, I have one question. Yeah, meantime I'll ask you. So this is regarding this basin hopping. So how is it different from the existing minimization algorithm, or let's say, for example, simulated annealing?
For example, which did you mention?
Yeah, I mean existing minimization algorithm or simulated annealing.
So simulated annealing could have been another approach. So the standard algorithms that are implemented in, like for example, VASP, those are local minima finding algorithms, right? Conjugate gradient or something like that. So it will be stuck in the local minima. But simulated annealing could have been another approach. But basin hopping has been very successfully applied to these nanoparticle systems. So that was one reason why we chose this. So there are a couple of other options, as you mentioned. Simulated annealing is one. Genetic algorithms can also be applied to something like this. Yeah. But basin hopping, so I think there are a couple of advantages. It's very easy to implement. You can implement it, and if you want to make any changes, and if you want to couple different types of codes, because this project involved interaction between different codes, some DFT codes, machine learning codes, and also some custom code for running basin hopping. So that was very, very simple to do, I would say. So yeah.
Okay. We have a question from Vaishali, and question is, was the propane dehydrogenation also sampled using ML potentials? If yes, then how many active cycles did it take?
So the work that I've shown you over here, in that we did not train any machine learning potentials with propane, but I have trained potentials with propane on platinum clusters. So propane on top of platinum, supported on Lumina. And how many cycles did it take? So I think for a system like that, if I remember correctly, so I used a different active learning algorithm in that system. The idea over there was you randomly generate a few configurations first, train preliminary machine learning potential, and then use that potential to run MD trajectory about a nanosecond long. And then we have some criteria of terminating that potential, that trajectory if it encounters configurations which are too outside of the training set. And I think it took maybe, I don't know, I think 10 days, give or take. I mean, these start to take a little longer once you start adding like more elements. And then also if the molecules are very floppy, which propane, like for example, is. So if I correctly remember, maybe more than a week, at least. Yeah.
Okay. The next question is from Sudeep. He asked, did you consider defects in the silica? And yeah, the follow-up question is the silica periodic or nanoparticle?
So in terms of defects, no, we didn't really study or take into consideration defects while we were making our models. But the silica models in my talk, as I had mentioned, these silica models, the way that we make them are very protocol dependent, right? We might change the protocol and we'll end up with a very different distribution of the silica surface. So for some of those parameters, you end up with silicas which have a lot of defects on them. But we decided not to use those models for now, at least. I mean, that could be another complexity that could be added in the future if we start looking at defects, because for some cases you do start forming these tri-coordinated silicon atoms, or forming penta-coordinated, like silicon is naturally 4-coordinated, but then in some silicas you start seeing like a population of tri-coordinated or penta-coordinated. So at least for this modeling work, we've not delved into that complexity. And your second question, so these models are essentially periodic, like they are pretty large, I think about 20 angstroms by 20 angstroms, X and Y, but they're periodic. But the way that we model them is we carve out a cluster from the periodic model and then we cap it by these by hydroxyl groups. So essentially, when we do the calculation, it's not periodic, but when we are generating the models, that's a periodic calculation.
Okay. The next question is from Tamugna. He says, you said the distribution of sites is non-Boltzmann. What exactly do you mean?
So whenever you have a Boltzmann distribution, the distribution is going to be given by exponential of minus beta times the energy of the system, right? Or if you look at a given configuration, if you know the energy of that configuration, the probability of you finding that in your system will be proportional to exponential of minus energy divided by kBT. But that is not true for non-Boltzmann systems. So if you have a system like that, if you have a Boltzmann distribution, then you can have, like, for example, you can a Monte Carlo method would work if you wanted to calculate averages, but it will not work if your system doesn't follow that probability. So over here, we do not know the probability distribution of the sites.
Okay. The next question is from Vaishali. She says, what about reaction intermediates? Did your initial training set had such configurations?
We didn't do any reaction intermediates, at least for the first part, where we only used a machine learning model to get the platinum structures. I'm not sure which part you're talking about. I think maybe you're talking about the second one, where we did have reaction intermediates, in the silica grafting example. Maybe I can go to that slide. Over here, like these are all intermediates, right? So 2 and 3 are, for example, intermediates. I don't know if you can still see my slides, but so the first one is the bare silica site, which is the reactant, and the final is you could think of all these 3 as intermediates. So we did calculate the free energies and fit them to some model. And in propane dehydrogenation, in the propane, I see. So in the propane dehydrogenation example, once we use the machine learning potential with Bayesian hopping to get the distribution of these stable platinum clusters on the surface, after that, at least for the plot that I showed you over here, I'm not sure if you can still see my slides, but like I'm on slide 12, where I'm showing you the turnover frequency as a function of the cluster shapes and sizes. There's no machine learning involved there. This is like actual DFT calculations where we use the nudge-elastic band method to calculate the activation barriers and things like that. So there's no machine learning involved, at least for that plot.
Okay. Next question is from Sudeep. Yes, could you please comment on the descriptors you have considered for ML?
So for this work, I used this machine learning potential called moment tensor potentials. So it's by a group in Russia. So it uses 2 types of basis functions. So you have these Chebyshev polynomials, which essentially give you information about the distance. Maybe I can pull up that slide. Let's see. And then you have moment tensor potentials, which encode information about the rotational symmetry around the.
Can you please reshare?
I see. Yeah, you cannot see my slides.
Yeah. No.
I'll reshare again. I thought I was still sharing. See. Can you see them now?
No, we see the last slide, probably questions.
Oh.
Yeah.
I'll stop sharing and sharing. I'll share again. So I've stopped sharing now, and I'm sharing again window. Oh, I see. Maybe I see what the problem is. Can you see it now?
No.
Let me exit the presentation mode. How about now?
Yeah.
Okay, you can see it now.
Yeah,
right.
Please go to the full screen mode. That would be good.
Yeah. Can you see the full screen?
Yeah, now we can see.
So I don't have a picture of, so yeah, over here I have a picture of the Chebyshev polynomials. So I mean, these are essentially used to encode the radial information, like depending on how far away you are from, so the atom. So this encodes that information, and then they have something called moment tensor functions, which essentially encode the information around the radial information around the atom. So let's see if I have I might have a few equations at the end that I can show you. Not sure if I have them here. Yeah, so this is how it works. So essentially, you take the full system energy, and then you partition it into atomic energies, and these atomic energies are then represented in terms of these basis functions, which are composed of these moment tensor functions, which encode radial information, and then you have these Chebyshev polynomials, which give you the radial information, and then we minimize this loss for energies and forces, and also stresses in some cases. Yeah.
Okay. Yeah, I have another question regarding your silica surface. So, what was the ionization state on the surface? I mean, what was the protonation states for different silicon-bound oxygens?
So all of these are saturated bonds. As I said, we chose materials which had no defects, mostly, or very minimal defects. So all of the oxygens are bonded on the surface to one silicon, and then to one hydrogen atom. Yeah.
Okay. Let me see. Okay. Yeah. Yeah. If there are no more questions, yeah, I take this opportunity to thank Dr. Salman for the wonderful talk. We really enjoyed your talk, and I'm sure that our audience would also, enjoyed listening to you. Now I will ask Dr. Seema to give a word of thanks.
Hi, Dr. Salman. I'm Seema. On behalf of everyone here at Pre-Science in Silico, I would like to extend you a heartfelt thank you for your outstanding talk today. As we have seen in fields like sustainable energy, fine chemicals, advanced materials, being able to model catalysts more effectively has huge implications, right? As you showed, for optimizing processes, developing new technologies. So your research is clearly pushing the field forward in a big way, especially as we continue to explore more atomically precise and efficient catalysts. So we are grateful that you could take the time out and share your insights with us today. We wish you continued success in your research journey, and thank you once again for such an insightful talk.
Thank you so much, and thank you for giving me the opportunity to present. It was a really wonderful opportunity for me, and I really liked it, and I got some really interesting questions, and yeah, thank you.
Okay. Thank you, everyone, for joining, and thank you, Dr. Salman. Bye-bye.
Thank you. See you.